So let us go to the chemical properties of chlorine. So if we go for chemical properties of chlorine, if you take, that is, first one is action of ammonia. So two different types of reactions takes place when chlorine reacts with ammonia. Actually, ammonia gas, when treated with the chlorine gas in excess, gives rise to nitrogen trichloride plus HCl. So 3 moles of chlorine gas you get. This is nitrogen trichloride. This is nitrogen trichloride. And now suppose if you are taking ammonia in excess, chlorine gas, so you can just take here ammonium chloride plus N2 gas, ammonium chloride in N2 gas, and here if you take 8 moles of ammonia, we can take 6 moles of ammonium chloride, and this is 3 moles of chlorine gas. So therefore you find that there are two different products which you are able to see, and this chlorine, if you take action of metals and non-metals, if you take metals and non-metals, action of metals and non-metals if you take, then we can take here, that is, suppose if it is reacting with copper when reacts with chlorine, you get cupric chloride, but not, yes, it can give cupric chloride, but it cannot give cuprous chloride. Then copper, when it reacts with, that is, if you take iron when reacts with chlorine, it gives FeCl3 but not FeCl2, because FeCl3, iron has +3 oxidation state which is more stable, and in cupric chloride copper has +2 oxidation state which is more stable. If you go for non-metals, for example, if you take phosphorus when it reacts with chlorine in excess, it can give phosphorus pentachloride 4, and this is 10, so 10 moles of phosphorus pentachloride it can give. And sometimes it also reacts with the sulfur when it reacts with chlorine, it forms sulfur monochloride, and sulfur monochloride in turn, if it reacts with chlorine, it gives sulfur dichloride. So balance the equation, then you can take that sulfur dichloride is obtained. This is sulfur monochloride. Similarly, this chlorine, it can have the other properties, like even if it is reacting with the other non-metals like phosphorus, sulfur, it can sometimes even react with the hydrogen, lighter elements. If you take hydrogen, H2 plus Cl2, in the presence of HCl gas also, HCl vapor, this is chlorine gas and this is hydrogen gas. Chlorine reacts with alkalis. Chlorine, if you take it, reacts with alkalis. Similarly, if it reacts with the action of alkalis, if you take, so sodium hydroxide when reacts with chlorine in the presence of cold and dilute condition, it gives sodium chloride plus sodium hypochlorite plus H2O. So take 2 over here, and sodium hydroxide, that is hot and concentrated, will give chlorine, that is sodium chloride plus sodium chlorate plus H2O, giving rise to, this is 5 moles of sodium chloride and 3 moles of chlorine gas and 3 moles of water. So it's a kind of disproportionation reaction that already we have done, no problem. Then likewise, if you take the same chlorine, it acts as a good oxidizing agent. It's a good oxidizing agent. H2S plus chlorine, sulfur is -2. It acts as an oxidizing agent. It gives 2 moles of HCl plus sulfur. So sulfur here, it is, the oxidation state of sulfur is 0. So here chlorine acts as an oxidizing agent and it converts the sulfide of hydrogen sulfide to sulfur, sulfur dioxide gets converted to sulfuric acid plus HCl. If you take, then we have 2 chlorines, so take 2 over here and take mark 2 over here. The reaction is balanced. Here sulfur is +4 oxidation state, and here sulfur is +6 oxidation state, and here the chlorine is acting as an oxidizing agent. The chlorine acts as an oxidizing agent. The chlorine acts as an oxidizing agent. Then in the next case, here also again the chlorine acts as an oxidizing agent. It converts the ferrous sulfate. Iron is +2 oxidation state, and here iron is +3 oxidation state. So here we have 3 sulfates and 2 chlorines. So therefore I am going to take 2 over here and 2 over here. Yes, the ferrous sulfate is getting converted to ferric sulfate, and in this way the chlorine can act as an oxidizing agent. And finally the chlorine can also act as a it can also act as an bleaching agent. So last one, fourth one, is as a bleaching agent. Chlorine, when reacts with water, it gives HCl plus HClO, hypochlorous acid. This hypochlorous acid, upon it is unreactive and it is reactive and unstable, so therefore it decomposes to give one HCl molecule and one nascent oxygen. So this nascent oxygen as a bleaching agent, as a bleaching action, this nascent oxygen will try to kill the bacteria, and it is also used in purification of water, in the filtration of water and in the purification of water. The nascent oxygen will act as a bleaching agent, and it is going to kill all the bacteria present in water, and it will allow the safe potable drinking water, and it converts the colored substances also to the colorless substances through moisturizing oxidation. So the next part of the discussion is oxy acids of chlorine. So we have 4 important oxy acids, that is formula, name, oxidation state, hybridization, then structure, then number of sigma and pi bonds. So formula, if you take, that is HClO, name is hypochlorous acid, okay. Oxidation state is +1, hybridization is sp3 hybridization. Then structure, if you take, yes, you can take the structure as chlorine. If you take it as 3 lone pairs, and it has actually between oxygen and hydrogen also there is one sigma bond. Between oxygen and hydrogen also. So therefore we can say that it's going to give the hypohalite ion. So therefore I can say the number of sigma bonds and pi bonds, there are 2 sigma bonds and 0 pi bonds. So formula, name, oxidation state, hybridization, structure, number of sigma bonds and number of pi bonds. So the first one we have done away. Then go for the second. If I go for the second, that is HClO2. If I take, then this is chlorous acid. It is chlorous acid and it is +3 oxidation state, and this is sp3 hybridization, and it is, take the structure of the chlorous acid. So it has 2 lone pairs. So because it is having 2 lone pairs, yes, I am going to take hydrogen single bond oxygen. So chlorine, if I take, then I have 2 lone pairs we have to get here. 2 oxygens are there. So therefore that is 1 double bond oxygen we can get over here. 1 double bond oxygen we can get over here, and we have 2 lone pairs. One lone pair is shown like this and another lone pair is shown like this. So again it is the structure and shape, sp3, here sp3, and this is bent molecule. So here the structure is that is bent shape. So we have number of sigma bonds and pi bonds. We have 3 sigma bonds and 1 pi bond, and also we have 2 lone pair electrons. Here we have 3 lone pair electrons. 3 lone pair of electrons. So therefore all that what we could say here is we can distinguish them clearly what is happening here. So next if you are taking, that is the third oxy acid, if you take the third oxy acid, that is HClO3, this is chlorous acid, oxidation state is +5, then here sp3 hybridization, this is pyramidal, sp3 hybridization, this is pyramidal, and here we have the angle, that is we have same structure almost, hydrogen single bond oxygen, chlorine, so double bond oxygen, and we have one pyramidal shape, so therefore one lone pair we can find here, and we have total 1 2 3 4 sigma bonds, 2 pi bonds, one lone pair of electrons. Then again if you are going to take the last one, that is fourth one, HClO4, if you take, this is perchloric acid with +7 oxidation state, sp3 hybridization, tetrahedral, and the shape is going to be hydrogen single bond oxygen, chlorine, we have double bond oxygen, and double bond oxygen, and here also double bond oxygen. So 1 2 3 4 5 sigma bonds, then 3 pi bonds, and 0 lone pair electrons are there, and it is tetrahedral in shape, perchloric acid. So here what I can say is this is the strongest acid in aqueous solutions, and this is the weakest acid in aqueous solutions. It is the weakest acid in aqueous solutions, and this is highly unstable. It is weakest acid, unstable, more reactive. So if it is more reactive than hypochlorous acid, it gives one hydrochloric acid and one nascent oxygen. Perchloric acid is the strongest acid, so it gives the weakest conjugate base. And this is perchloric acid. It is the weakest acid, so it is going to give the strongest conjugate base. So what is the strongest conjugate base means? Here you can just take the reaction. HClO gives rise to ClO minus plus H plus ion. So this is hypochlorite ion is the conjugate base. And if you go for HClO4, it is a strong acid, so it has to give the weak conjugate base ClO4 minus. This is the weak conjugate base. ClO4 minus is the weak conjugate base. This is strong conjugate base, and this is going to become the weak conjugate base. Is the tendency of perchloric acid, which is giving the weak conjugate base, and tendency of the weak acid giving strong conjugate base is what we can make a comparison between the oxy acids of chlorine. And these are all the different shapes and structures of the oxy acid. So we have 2 lone pairs on each oxygen. Here also we have 2 lone pairs on each oxygen. Here we have 2 lone pairs. Here also 2 lone pairs. Here also 2 lone pairs. Wherever you take oxygen, there you are supposed to show the 2 lone pairs, and this is the complete information where you can gather from the oxy acids of, that is, chlorine. So name, then oxidation state, then hybridization, and the structure and number of pi bonds, and also number of sigma bonds. So here let us go to the next part of the discussion, that is the next chapter, that is 18th group, noble gases. So these are otherwise also called, they're also called inert gases. Inert gases because of their stable electronic configuration, that is completely filled electrons in their orbitals. Then these elements, they are called as zero group elements. Zero group, these are also called zero group because their valency is equal to 0. Then these are also called as Eurogens because of their availability in atmospheric air. Then if you go for elements, if you are going for the elements, we have helium, neon, argon, krypton, xenon and radon. Except radon, rest of all the elements are the lighter noble gas elements. Radon is the radioactive element. So helium atomic number is 2, neon 10, argon 18, then krypton 36. This is 54 plus 32, 86. 86 is radon, and here the configuration is 1s2. Here the configuration is helium of 2s2, 2p6. Then here it is neon of 3s2, 3p6, and this is argon of 3d10, 4s2, 4p6, and again this is krypton of 3d10, 4d10 of 5s2, 5p6, and this is radon, that is xenon of 4f14 of 5d10 of 6s2 of 6p6 is the configuration. So therefore you are finding that except for helium, rest of all the elements, their general electronic configuration is ns2 np6. It proves that because the differentiating electron is entering into the p orbital, because the last electron is entering into the p orbital, so therefore we can call them as p block elements. These elements are p block elements, but again helium is an exception, because helium, the differentiating electron is entering into the s orbital, so helium is an exception. So except for helium, rest of all gases, ionization of the rest of the gases is very difficult, because the ionization of the rest of the gas are very difficult because of the stable electronic configuration. Large amount of energy is required. But even the helium also, you cannot directly ionize the helium. This helium is actually arised, it's going to originate from the radioactive substance. So radon, if you take, it is radioactive, it is a radioactive element, distinctly radioactive element. So this radon, it undergoes radioactive disintegration. 86, it emits an alpha particle. So say for example, you can take 226, radium 226, if you take, it is going to emit an alpha particle. If it is emitting an alpha particle, it is going to be 84, that is polonium of 222, polonium of 222 plus 2He4 is the alpha particle which is generated. So here this 2He4 is the alpha particle, it is nothing but the alpha particle. This alpha particle is doubly charged helium nucleus. This is helium nucleus, and this helium, it undergoes self ionization to give He2 plus 2 electrons. And at the same time, if you go for the other properties of noble gases, they are insoluble in water. Then they have low melting points and boiling points. The reason is because they have weak van der Waals forces. And all the elements, they are monoatomic gases. Because of the presence of weak van der Waals forces, of the existence of monoatomic gases, they have low melting point and boiling point. So it was actually first the compound of the first compound of the the noble gas elements, that is O2, O2 plus of Pt F6 minus, this is dioxygen, but dioxygen of hexafluoroplatinate. The first complex was isolated where in which it contains the oxygen gas, but later, that is Bartlett, it was actually Bartlett who has isolated the first noble gas compound. That is nothing but, the first noble gas compound is nothing but xenon hexafluoroplatinate. This is the compound which was isolated by the Bartlett, the first noble gas element, that is xenon hexafluoroplatinate. And if you go for the compounds of noble gas elements, here particularly we should be bothered about compounds of noble gases. If we take compounds of noble gas, one is halides. In halides, if you can take xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. And in the case of oxides, we have XeO3, then XeO4, then XeO2 of F2, XeOF4, and so on and so forth. These are all the different oxides of the xenon, and these are the halides of xenon. So now let us study the internal structures of the xenon difluoride and xenon tetrafluoride and xenon hexafluoride. So here, if you go to the preparation and properties of xenon compounds, you can very clearly observe that we are able to prepare all the halides of xenon. One is xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. Here, in the first case, if you want to prepare xenon difluoride, here xenon reacts with the excess of xenon reacts with fluorine at 673 Kelvin of temperature and 1 bar of atmospheric pressure to give xenon difluoride solid. And if we want to prepare xenon tetrafluoride at a temperature of 873 Kelvin and 1 bar of the atmospheric pressure, xenon and fluorine, they are in the 1:5 ratio, and it gives xenon tetrafluoride. And again, if you want to prepare xenon hexafluoride, again in 1:20 ratio, xenon reacts with 3 moles of fluorine to give 1:20 ratio at a temperature of 573 Kelvin and 70 bar of pressure. You can see that the pressure, by the time we reach the xenon hexafluoride, the pressure is increased and the temperature is decreased. So that means in 1:20 ratio, the most favorable condition for the preparation of hexafluoride of xenon is, that is 70 bar of pressure and 573 Kelvin of temperature is what we have to keep it in mind. And when we are going for the chemical properties of the halides of xenon, we should be a little bit careful. In the case of xenon difluoride, when 2 moles of xenon difluoride are able to react with 2 moles of water, then I think it disproportionates. It's not exactly disproportionating. For example, here the xenon is +2 oxidation state, and here the xenon is 0 oxidation state. So the xenon is undergoing reduction. The xenon is trying to reduce itself from halide to elemental xenon, and you get one more fluorine, that is hydrofluoric acid, and also oxygen gas is evolved. And in the case of xenon tetrafluoride, here the xenon is +4 oxidation state, and here the xenon is +6 oxidation state, and here the oxygen is +1 oxidation state, and here the oxygen is 0 oxidation state. So this is a kind of the redox reaction. Second one is a perfect example of redox reaction. Of course, the first one also, it is a perfect example of redox reaction. The dioxide difluoride is trying to oxidize. This is acting as an oxidizing agent. It is oxidizing the xenon, which is in the +4 oxidation state, to xenon in the +6 oxidation state, and by itself it is getting reduced, because you can see that the oxygen atomic number is 0. And sometimes, interestingly, these halides of xenon, when they interact with the halides of the phosphorus, pentahalides of the phosphorus, the xenon difluoride, they act as Lewis acids. That means they are Lewis acid means electron pair acceptors, and donors means electron pair donors. That is, you can see that they act as Lewis bases. So the interactions between Lewis acid and Lewis base interaction always leads to the pair of complexes. One complex is cationic complex and the other one is the anionic complex hexafluorophosphate, hexafluorophosphor anionic complex, and xenon fluorocationic complex is formed. So in that way we can also prepare some cationic and anionic complexes. And if you go for xenon tetrafluoride and xenon hexafluoride when they are subjected to hydrolysis, so this is a kind of disproportionation reaction. Xenon tetrafluoride plus 12 moles of water. Here the xenon is plus 0 oxidation state, and here the xenon is plus 6 oxidation state. So it's very clear that the xenon tetrafluoride is undergoing disproportionation reaction. I can say that this is definitely a disproportionation reaction, definitely disproportionation reaction. And yes, because plus 4 to 0 and plus 4 to plus 6 oxidation state is taking place, so therefore we can say that it is disproportionation reaction. But here what is happening here is there is no change in the oxidation number for xenon. In the next reaction it is plus 6 oxidation state. Here also xenon is undergoing plus 6 oxidation state, so there is no change in the oxidation state. Here also the xenon hexafluoride, xenon is plus 6, and here also xenon is plus 6 oxidation state. So 2 moles of HF is the byproduct, and this is how you need to remember the various chemical properties of xenon. And now let us go to the structural aspects, including their hybridization involved, and let us try to study them in brief. So the next part of the discussion here is structural aspects of xenon compounds. So if we go to the structural aspects of xenon compounds, here we have different structural aspects. Like let us go for oxides. If you go for oxides, we have XeO3 and XeO4, and also you can take XeO4, and you can take even XeOF4 you can take, and even you can take XeO2 of F2 also we can take. So how can we just identify the structure and hybridization of the given oxides of fluorine? For example, if I am going to take with the XeO3, underline xenon, apply the formula H is equal to half of V plus M. So V is the number of valence electrons of the central atom, and M is the number of monovalent atoms present in the oxides of xenon. So here what is happening here is like if I am going to take H is equal to half of, it is xenon number of valence electrons are 8, and oxygen is not a monovalent atom, oxygen is always a bivalent. So in the place of M value, M is a monovalent species, so because the oxygen is bivalent, so let us take the M value 0. So here interestingly H is equal to 4, you are going to get H is hybridization, V is the number of valence electrons of the central atom, and M is the number of monovalent species present in the given molecule in its adjacent form. So H value is 4 here for XeO3, but you can find that the number of adjacent atoms are only 3, so therefore it is very clear that it forms when H value is 4, the number of adjacent atoms should be 4, but only 3 are there, so therefore that means it has one lone pair, compulsory one lone pair should be there. One adjacent atom is missing, so one lone pair, presence of one lone pair plus 6 bond pairs, because you find that here xenon has 8 valence electrons, so 6 bond pair electrons can be observed. So therefore if you go to the structure of XeO3, so you find that the structure looks like this. This is the structure of XeO3, and you can outright say that this is pyramidal in shape. You can outright say that this is pyramidal in shape. Pyramidal. And if you go for similarly next for XeO4, if you take H is equal to half of V plus M, number of valence electrons in xenon are 8, so therefore half of number of valence electrons of xenon are 8 and number of monovalent atoms are 0. H is equal to 4. 4 means it is sp3 hybridization, and it is tetrahedral. It is tetrahedral in shape, so therefore you can go to the structure of xenon. So here we can take here, that is, so this is xenon tetroxide. This is definitely tetrahedral in shape, and you have here one more thing. Here we have 3 sigma bonds, sigma, sigma, pi, then this is pi, and this is sigma, and this is pi. So we have 3 sigma and 3 pi bonds are present in the case of the xenon tetroxide, and here we have 4 sigma, 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 and sigma. You have pi, 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 and pi bonds. So we have 4 sigma bonds, comma 4 pi bonds, which is tetrahedral in shape. And here you don't have any lone pair of electrons in the case of XeO3 and XeO4. So here also XeO4. Okay, fine. So that means we have completed the oxides of xenon. Now we'll go for XeO4 and XeO2F2. So if you go for XeO4, suppose for example if I am taking XeO4, if I am going to take, then H is equal to half of V plus M, H is equal to half of number of valence electrons are 8, number of monovalent atoms are 4, but oxygen is bivalent, so I am taking only 4, so H is equal to 6. We are getting 6 means one adjacent atom is missing, so therefore we can say that this is square pyramidal. It has one lone pair and 6 bond pair of electrons, 6 bond pair electrons you can find. So if you go to the structure, it more or less looks like this, that is fluorine, 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 and it is in the square planar shape, and you find that one lone pair, you can just show it at the bottom, and here I mean one pair of electrons with respect to oxygen we can show at the bottom. And yes, of course the hybridization is sp3 hybridization, sp3d2 hybridization you observe in the case of the XeOF4 molecule, and XeO4 molecule we have observed. And now I think you can go for XeO2F2 also. You can take XeO2 of F2. If you take H is equal to half of V plus M, which is equal to half of number of valence electrons are 8 and number of monovalent atoms are 2. So 2, and oxygen is not a monovalent, it is bivalent. So H is equal to, that is 10 by 2, which is equal to 5. 5 means again one adjacent atom is missing. So therefore we can take, of course the hybridization is sp3d hybridization. The hybridization is sp3d hybridization, but we have one lone pair and we have 6 bond pair electrons. So therefore if you go to the structure, you can take the structure like this, that is you can take, that is 2 oxygens, we can just show it like this, and 2 fluorines we can take. It is a square planar shape, and one lone pair you can show it like this, and another lone pair like this. This is square planar shape. It is square planar shape. This is what we can identify in the case of all oxides of xenon. So if you go to the halides of xenon, that is second part, halides of xenon. If you take, we have XeF2, then XeF4 and XeF6. All I can say is, like, if you go for XeF2, if I can take XeF2, I can say that xenon difluoride structural aspects, if you take in the first excited state, of xenon, it undergoes sp3d hybridization, and it gives a linear shape which contains 3 lone pairs at equatorial position and 2 bond pairs and in the axial position is what we need to remember. And overall we are calling this as linear shape. It is linear shape because the three lone pairs which are at equatorial position, they are separated at the rate of 120 degrees. So therefore if you go to the structure of, and if you calculate the hybridization value also, H is equal to half of V plus M. If you take, that is xenon, number of valence electrons are 8, and fluorine is number of monovalent atoms are 2. So H value is 5. 5 means it should be definitely trigonal bipyramidal shape, but because there are only 2 adjacent atoms, as already I told you, it has 2 adjacent atoms. If it is having 2 adjacent atoms, then 3 adjacent atoms are missing. So that's why we have 3 lone pairs and 2 bond pair of electrons. And if you look into this, 5 value means definitely it is sp3d hybridization and trigonal bipyramidal shape it should have, but because 3 adjacent atoms are missing, so from here I can directly give you the structure. That is, I can take 2 fluorines in the same plane, and the rest of the 3 lone pairs, they are trying to occupy the equatorial position like this. They are trying to occupy the equatorial position like this. They are in the trigonal bipyramidal plane. All I can say is yes, they have the trigonal bipyramidal plane. They have, but because they are 120 degrees separated apart, whatever the kind of repulsions are operating between the 3 lone pairs in the xenon difluoride, they are quite negligible. That's why we can say that the shape of the xenon difluoride molecule is definitely, that is linear shape. So this is one important point which you have to keep it in your mind. So XeF2 is done. Now we'll go for XeF4. If you go for XeF4, again, yes, in XeF4, in the excited state 2 of xenon, it undergoes sp3d2 hybridization, but here only 4 adjacent atoms are there. So I can say that it has square planar shape with 2 lone pairs in the axial position, and the rest of the 4 bond pairs are in the equatorial position. They are in the equatorial position. So therefore here we can take, that is xenon. So take the shape of the xenon here, xenon tetrafluoride. So here fluorine, and two lone pairs are there. So here we have 2 lone pairs. These are the 2 lone pairs we have in the case of xenon tetrafluoride. That's why we are calling it as, the shape we are calling it as square planar shape. Now going back to the last one, that is C, XeF6. If you take XeF6, that is in the excited state 3 of xenon, it undergoes sp3d3 hybridization. Then this is distorted octahedron. It has a distorted octahedral shape with the one lone pair and 6 bond pair electrons. So therefore here we can take the structure in this pattern, that is because it is sp3d3 hybridization. So the best thing what we can do here is distorted octahedron. So because it is distorted octahedron, it has to lie in the pentagonal bipyramidal plane. So that's why what I am going to do here is, like, I am going to put it somewhere like this. I am going to create a pentagon like this. This is a pentagon, fluorine, and also fluorine here. So the pentagon is created, and we have one fluorine outside. So I am going to take one fluorine below like this here, and we have one lone pair also. So this we can take it as distorted octahedron is the final shape of the XeF6. molecule. And from the structure also it is very clear that definitely one lone pair is existing in the case of XeF6 molecule. So if that is the case, then I can say like this: XeF2, XeF4, XeF6. So we have here we have lone pairs, bond pair electrons, lone pair and bond pair electrons. So if I take here halides of xenon, so this I will take XeF2, this I will take XeF4, and this I will take XeF6 if I take. So you have to keep it in your mind that XeF2 contains 3 lone pairs and 2 bond pairs, then here 2 lone pairs, and XeF4 4 bond pair electrons, and XeF6 1 lone pair and 6 bond pair electrons are there in the case of halides of xenon. So this is what you have to keep it in your mind: halides, lone pair electrons, and also bond pair